I wasn't really planning to talk about tree loops, but there seems to be a general interest in at least understanding some of the calculations, and I've been reading in the past 2 hours just to put the calculations in my short-term memory, and but yeah, perhaps there will be some gaps in my memory, and I apologize in advance for that. So, and one of the reasons why I wasn't planning to discuss about the tree loops, tree loop amplitude, is, well, all this time I've been praising the beauty of pure Spinor superspace. That well, you have the 3 lambdas and a bunch of superfields with the pure Spinor bracket, and that's they lead to compact expressions, and you can easily verify their steam invariance and all that. But it turns out that the calculations with the non-minimal pure Spinor formalism, they are not very optimized for this kind of analysis, and so let me exemplify what I mean by that. In 2004, Nathan computed the one-loop 4-point amplitude with the minimal pure Spinor formalism, and in a few lines he obtained the kinematic factor, this one, which I noted K1 in a previous lecture, and I said, well, that's a nice expression, right? And in 2005, he computed the same one loop amplitude for 4 points using the non-minimal pure Spinor formalism, and the expression for the kinematic factor, well, this is the standard T8 f to the 4th, and in the non-minimal formalism, that you get something that looks like this: covariant derivative v1 down to 2 down to 3 and W4.
What is MPS?
What?
Minimal pure Spinor.
Oh, yeah, minimal pure Spinor, and this is the non-minimal pure Spinor version. It's still okay. There is a lambda bar now. That's the lambda bar that Nathan explained to us in a previous lecture. But now you still need to do some computation, because you need to act with the covariant derivative on these superfields, and acting with the covariant derivative on V1 is not really that nice. You need to use the equation of motion and BRST integration by parts, but then there is this lambda bar, and in the end you need to get to arrive at some expression of lambda where a lambda is contracted with lambda bar, and then you will find that expression here, the minimal pure Spinor formalism expression. You can do these calculations, and yeah, the result is you can do the calculations, but it's not really this expression here is not really in a form where you can simply type things in your computer and press enter, and then you get some the component expansion, for example.
So how are you going to minimize the expression? you are doing something with lambda bar. Yeah. What did you say? How to go to minimal expression?
Okay. Okay. So these are like 2 pages of covariant calculations. Nathan had an argument using U5 decompositions, but then well, it's not covariant anymore, and so it's not that straightforward. The covariant calculations to prove these, I wrote them in my thesis. You can find it there in 2009, I think. It's on the archive.
And what is D?
D is the covariant derivative.
Okay. Yeah.
So and yeah. You can do the calculation, but it's not that nice. So at 2 loops, the same story happened. In 2005, they computed with the minimal Spinor formalism, the 4-point amplitude, and he got this expression here. It's a beautiful expression, and you can analyze it, compute the BRST variation, and life is beautiful here. And in the non-minimal pure Spinor, he also computed the same amplitude in 2005, and the expression looks like this. You see, I don't even remember by heart. MNP D, then lambda bar, gamma D, E, F, D, lambda bar, gamma Q, R, S, D, and then multiplied by, so it continues here, lambda gamma M, D, E, F, Q, lambda N, 1, 2, you see that there's not even enough space to write this stuff. Okay, that's the expression. You can also, he also showed that it was equivalent to the old one by using U5 decomposition of the Spinors. And yeah, but if you want to do the computation covariantly, since well, we live in SO 9,1, right? So you want to do the calculations covariantly, and it's a bit of a mess because there are too many covariant derivatives and too many lambda bars, and in the end you want the lambda bars to appear like that, such that you can use the lambda 3 beta 5 measure here. Okay, these calculations were done covariantly in a paper with Umberto in 2010, and they are hidden in one appendix. So it's not something that you are proud of, but it's there. And so at 3 loops, the analogous, so the 4-point amplitude was completed in 2013, and the one of the kinematic factors there, it's something like T 1, 2, 3, 4, and the expression for it, I'm just going to write it just to scare you. That's the point here. Lambda bar D, E, F, D, letters start to run out of letters to write this. A, T, E, F, N, lambda, gamma, B, G, E, I, T, lambda, and another 5, 4, it's U, Q, R, S, N, lambda, and then finally the superfield. Okay, well, the only nice thing about this structure is that you get a multi-particle superfield there, but
What are the indices after GHI?
GHIT,
Above that line, first line.
GHINNP. Okay, so I probably made a typo in copy and pasting these, and it's an exercise to find which index I screwed up. So you get the point. It's a mess, and this is where the theory versus practice quotation applies. You want to get the amplitude out of these things, and you need to face these expressions. You need to really compute these things, and then you need to square them and all sorts of stuff. But then, studying these multi-particle superfields and all that, I came across an expression which is this one, and then you anti-symmetrize 3 and 4 here. And where now this is the multi-particle guy, but in its higher mass dimension form. Where that's why yesterday I mentioned it briefly. That this guy here, for example, with an index m is defined as delta m w w1 2 also. So you get that it's a higher mass dimension because of the momenta here, but you also get a deconcatenation contribution of this form, something like this, and then anti-symmetrizing in 1 and 2. And then this expression here, you can easily compute the BRST variation. You get a nice BRST algebra like Q T1, 2, 3, 4 is S1, 2, T1, T2, 3, 4 minus it's 1 and 2. Okay, so I realized that this is, but that's the point. So it would be really nice to find what's the minimal pure spinor version that gives you this kinematic factor, because it has been checked that using this expression here is equivalent to using that one. But that one here is really awkward to work with. So yeah, but so here, if if the computation was done in 2013 and we had this expression arising naturally, then I would be very happy to talk about it. But now it's still a bit, it's a bit of early computation. But that's the price you pay for getting the coefficients precisely. Because in this in the minimal setup, you do the calculations, but it's only up to a overall constant. And in the non-minimal version, you get the coefficients in a very precise manner. So that's so that's one motivation for avoiding a bit explaining about this, but let's hope that things will get better in the future.
So the top line, is it proportional to lambda bar or whatever, 6 or something like that? No, 6.
Oh, the mass?
Yes.
Yes.
It is proportional to lambda bar to the whatever.
Yeah, so this one, and yeah, the computations showing this precisely are in the appendix of the paper, but there is this lambda bar to the power 6. So it should have 6 lambda bars from the big ones and 9 lambdas, and then you get lambda bar to the 6. And then lambda 3, beta 5 here, and then you can compute the components and check S-duality.
Sorry, so the thing that's left over is just written in terms of the W's and the lambdas.
Yes.
So why didn't you just write that? Why did you write the whole thing? I don't understand. What? In that case, on that board you wrote them both. And the second one was much simpler than the first, right? NPS.
Yeah, the first one is simpler than the second.
So what is NPS for that one?
That's what I don't know, but I suspect that that's the expression.
You just said it, proportional to lambda bar to the 6.
Well, this expression, I'm not saying that.
The top one.
Yeah, but I'm not saying that this expression here came from this one.
No, but you said the top one can be written as lambda bar to the 6 times
Yes,
something.
yes.
What is the something? That
It's also a mass.
But it's just written in terms of lambdas and
Yes.
superfields.
Yeah, but it is still. Okay, I should say that it was a mess when these computations were done in 2013 because I didn't know about this high mass superfield, but now, well, if I look again at the computation, perhaps I will be able to identify that expression. But okay, but that's okay. Yeah, it's well. There is some work to be done here in simplifying the computations.
So this power of lambda bar is something to do with 3g minus 3 factors or?
Yes, yeah. Yeah, the 6 there is because it's a 3 loop and 3g minus 3 is 6. Yeah, so here it's 1 and 2 loops is 3.
From these expressions, is it easy to see that the number of momentum which come out at leading order?
Oh yeah. So for example, it's you can either analyze it here as we did in the paper, or you can analyze it here. So let's do it here because it's simpler. So you get 3 powers of momentum for free because it's of that. So you have 3 powers of momentum and W1, 2, W3, W4. Something like that.
This is the downstairs expression.
Yeah, the downstairs. a simplitude of 3 factors of momentum, and
But then you don't have W hat.
no, well, it's I'm just looking at this
Okay.
part here, where the momentum, the index n, the vector index is carried by a momentum. So you get an expression like this, and W12 has the dimension of a WF. So, okay, let's read something like that. So the expression here is momentum 3, and then WF. So you want to take the F components out of this expression, and then take 1 theta from here, 1 from here, 1 from here, and 2 from there. And then you get F, then momentum F. So the whole thing is momentum to the 4th power. And then when you square this, as in the closest thing, you will get e to the 8th to the 4th. But then this guy here still comes with a colliding singularity in the worksheet. So in the computations, this guy appears with a del G12, and then when so that you get an integral of this guy with a Computations factor, and then the leading term, something like that. There is an inverse power of Mendelssohn, so, and then that's why you get this. Okay, so the prescription to compute the 3 loop amplitude is there are 6 factors of this kind, like this, and then the regulators, 3 of them, one for each zero mode, and then the external vertices. And then, yeah, it sounds like that. And the regulator is it's as Nathan was explaining, is something like this, also as U1 plus the big ghost, the terms that will contribute in the calculation are 1/2 lambda.
The ends are what?
The ends are the zero mode regulators.
I see those ones.
Yeah.
N1, N2, N3, is it?
Yeah, N1, N2, N3, because there are the 3, it's 3, and for each genus you have a set of homomorphic monoforms.
Okay, and then what is the next equation? N what? What is the superscript?
It's
N
I.
okay.
So I is capital I is 1, 2, and 3. for the loop order. And then there is another term which and then the other terms do not contribute today, at least. So these are the two terms from the big O's that contribute, and
So you have one lambda integral, so it's, you raise it to 3.
oh, I forgot to write down that everything is inside pure spinor bracket, and I need to mention all the zero modes associated with that.
But you write n1, n2, n3,
Yes.
this becomes e to the minus 3 lambda lambda 1, or you only sum over I.
I'm summing only over I.
Okay, so this lambda lambda 1 is only one factor, not 3, right?
Yes, yes.
So that product is basically N1, N2, N3.
Yeah, that's right, yeah.
3 wouldn't change the answer if you had 3.
That's it. Presumably, physically there is only one, or
It doesn't matter, because the coefficient in front of the exponent doesn't affect the answer.
Okay.
Oh, yeah.
Oh.
But
the overall coefficient or the coefficient of each term doesn't matter.
The coefficient in the exponent doesn't matter.
yeah, so if I think that's what he's saying. If I multiply everything by rho, that doesn't affect anything. But it's safer just to do things correctly. So yeah, so in principle, writing this is a bit sloppy.
I don't know what you mean by sloppy, but it doesn't matter. As long as the thing in the exponent is BRST trivial and it regularizes, that's all.
But
Yeah.
the point is that there is a difference between summing over I, keeping the lambda lambda bar fixed, and multiplying the whole thing. See, you are not multiplying the whole thing by 3, right? See, what he has written, lambda lambda bar and r theta coefficient will get multiplied by 3. The rest will not do.
I understand, but when he writes N1, it's actually the product of two BRST invariant objects. The lambda lambda bar minus r theta is BRST invariant by itself,
Oh, I see.
so it doesn't matter.
And these are very trivial.
So this sum over ST, that is also there is trivial by itself. Sum over ST and W and W bar.
Yeah.
This SI, DI, W, also by itself. Exponential is trivial, is trivial. The lambda lambda bar plus
Last term.
yes, it's BRST exactly.
Lambda lambda bar plus theta r.
The BRST. And the remaining part, that's what BRST. And the remaining parts, that's what BRST is. The SI, DI, W,
Right,
Separately
right, separate.
for each I.
for each.
So in these calculations, whenever you see a form with one variable, you need to do this expansion here, where this guy will act as OPEs, and these are the zero modes, and the variables in the pure spinor and the non-minimal, they have the fermionic ones are these ones, and they have the zero modes, non-zero modes, and zero modes are 11G, 11, 16G, and so these are the non-zero modes. And the zero modes. Just stating the number of them, and this is what Lee was telling us in these lectures. And then there is also, so these are the fermionic, and then there is also a set of bosonic variables, and they have some associated zero modes and non-zero modes, but I'm not going to write them here. And finally, I need to the pure spinor bracket over there. Well, first you need to remove the non-zero modes with OPX, and after you do that, the bracket means that you need to integrate over the measures that Nathan was mentioning. The lambda bar, BR, the filter, and then BEI, oops, it's a spider. Okay, so these are all the variables that you need to integrate. They are the zero modes that you need to integrate. And for each one of them, the measure looks like, I'm not going to write all of them, but let's do maybe a three. That's equal to C lambda, and then epsilon alpha 1 to alpha 16, and then B lambda alpha 6 to alpha 16, and I'm just going to write down the measure for the corresponding T alpha 1 to alpha 5, and then epsilon D down to something like this, where the epsilon indices are contracted.
That is D lambda alpha 6.
Yeah. Alpha 6 to alpha 16. And this T, alpha 1 to alpha 5, is lambda gamma m alpha 1. It's the lambda 3 theta 5 measure without the thetas. And you can show that because of the pure spinor constraint, this tensor is totally antisymmetric in the spinor indices. And the coefficients here, they, well, and then there are all the other measures, but this is meant just to give you a flavor. So there is some power of a prime, some combinatoric factor, and then the area of the Riemann surface, 11/2, and CW and then I need to tell you what, okay, so this is the area of the Riemann surface, and this is the determinant of the input. So the ZG is 1 over square root of the determinant of the 2 times the imaginary part of the period matrix. And by the way, I should say that this except for the area factor and these factor of Z, the period matrix, these normalizations were fixed in a paper of Humberto Gomes. He worked out these normalizations, and you should take a look at that paper to get all the and I just should mention, well, this 4 pi squared is related to the measure factor of a quantum mechanics phase space, where you have some x e over square root of 2 pi square root of 2 pi. This is just a combinatoric factor related to the 11 guys there, so it's 11 factorial there. And then the measure, the factor of the area is because this is a conformal weight 0 variable in a Riemann surface, and it needs to be normalized. So the 0 mode of this variable needs to be normalized by the area of the Riemann surface. So that's why, because it's the 0 mode, then when you integrate these, it cancels the area. And this factor here is well, and then, well, this is a conformal weight 1 variable. So it's expanded in the homomorphic bond forms, and the homomorphic bond forms, there is this formula that you, when you integrate it over the surface, gives you 2 times the imaginary part of the period matrix, and when you change basis from these homomorphic bond forms to a set of, which is normalized, you will get a Jacobian factor which is related to the determinant of that imaginary part.
So relation relation with lambda 0 and the area of Riemann surface? I didn't quite understand.
What?
The area of Riemann surface and lambda 0.
Yeah, okay. Yeah, I was just going to, we explained this in a paper, the 2010 paper. But it's essentially that you expand the pure spinors in the eigen values of the Laplacian. So you get the zero mode, and then this is corresponds to the. This would correspond to something like the holomorphic one form, but for the form with zero variables, and then you get some expansion in terms of the eigenfunctions. So these are the eigenfunctions of the Laplacian. But then this guy here, well, you how can I say that? The norm of this guy and the Riemann surface square is the area of the Riemann surface. You integrate this over the Riemann surface, and it's a scalar. There is no z depends. So you just pick the area. The Riemann surface. So it's just I realize that this is just a sketchy argument, but you can read more details in the 2010 paper. But yeah,
so area is not given in terms of the period matrix.
What?
The area. Is it not given in terms of period matrix?
That's a good question, but at genus 1 it is, right? Because the genus 1, the area is tau 2.
Yeah.
But I'm not sure if it's true in general. Perhaps it is, but
eventually you will integrate only over the period matrix, right?
Yeah. So I was going to say that in the end, all these area factors cancel. So you don't even need to worry about it. Because when you consider all the measures here, the normalizations of the area go away. So as it should.
But this is the only place I've seen it appearing, AG, is in the C lambda.
Okay, but
source of other, there is other source.
Yeah, so you haven't seen it all. Yeah, perhaps I could. I could try to show to you how the area cancels, but it's not that complicated to see, but because in the end, the vector of the area is also okay. So the area, you get a positive factor of the area for a bosonic variable and inverse factor for a fermionic variable. So you have the thetas also, so you get an inverse factor of the area there. And there will also be, okay, so let me just write, you get C lambda bar with, it will contribute like area to the 11, and then CR will contribute area 11 over 2, and C theta, minus. And C theta is area of minus 16 over 2. And then these guys here will appear squared in the closed string amplitude. So you need to square all of this, and you will probably get the area with a factor of 5 here. I'm not going to do these trivial calculations in front of you because I will probably get it wrong. But that should come from here. And then when you compute the correlation function of the exponentials, you will also get a factor of the area inverse, because it will be integrating over dx over the surface, and there are some steps that you need to show. But I guess that these computations here, well, you can look at the Polchinski book, for example. I guess you can observe the area factor there, and it's also explained in the paper I'm back.
Yeah. So the second, also the third line, that is also CR.
C theta. What? Kx. It's the plane waves. Okay, so believe me, the area cancels. That was one of the consistency checks that needed to be done. Okay, so let me just step back to see what needs to be said. Okay, so the Beltrami part is this one, integrate over surface, beta compacted with the Beltrami differential. And fortunately, you don't really need to know the precise parameterization of the Beltrami differential, because in the end, we are going to get rid of the Beltrami using a formula that looks like this. We integrate over the surface, and then that's del omega ij d tau I, and that's called how variational formula that will be simply stole from the mass literature, but and then you don't really need to worry about the Beltrami. And I'm going to show how to use these in a moment. So and these are the Teichmüller parameters that appear in the prescription. Okay, so I guess that we are done with the part that appears in the prescription, and now it's the part to start in the calculation. Any questions? Okay, so the first thing that we are going to do is to integrate the B ghosts. And we are going to see that once we do this, we will get the conversion from a parameterization where the Dice-Miller parameters appear to the period matrix. So that will be the del Z integration of the B ghost, and it's essentially using that formula. So okay, so as I said, there are two terms from the B ghost that will contribute, and I'm just going to show the analysis for one of them because the other is similar. And then so one thing that I need to say is that the whole computation here considers just the zero modes of the B ghost. That's the weak part of the calculation. The zero modes of the B ghost. But we showed in the paper that this is enough to get the low energy or the leading order contribution in alpha prime correct. So leading order alpha prime. If you wish, this is similar to considering the planar versus non-planar contributions that Nathan mentioned in this lecture. So this is like we are just considering the planar sector. So, and pushing these computations to higher powers of alpha prime is an open problem. So when we expand when we consider the zero modes of the B ghost, for example, for this part we get the expansion of B's like this, I from 1 to 3, and this factor here will become I'm going to use a compact notation to save some time. It's W1. And then that's one contribution, and then there's another one which is this one. And there are other ones where you simply sum over I and J and you get that. So the thing to note here is that this combination is essentially that one, just a shorthand notation. It's fermionic. This contribution is fermionic because B is fermionic, and R is fermionic, and 2D is bosonic. So there are 6 factors of the B ghost in the 3-loop computation. So when you multiply all of them, because of this anti-symmetry condition, the fermionic, you will get that the whole thing gets anti-symmetrized. And so let me just write down the formula too. So you will get that this part is equal to an anti-symmetrization of 1 to 6, and then I'm already going to use, okay, so we have the Beltrami there, and all of these will be multiplying the Beltrami. And we are going to use this formula here to convert to the period matrix. And when you do that, you get an anti-symmetrization of 6 indices, and then del E omega 1 to D tau 1 up to D33 D tau 6, everything squared, because it's squared.
So this is omega 1 1 and also omega bar 1 1. That's the point, right? I didn't get for it.
Yeah, this appears inside the. Okay, I forgot one. There is a holomorphic square here.
Because this involves all the components of omega, all the independent components of omega.
Yes, yes.
Omega 1 to omega 1.
Yeah, omega 1 1 to omega 3 3. And that's actually a very important point here, because you see that there are 6 independent components of the period matrix. It's the same number as the Teichmüller parameter, and so the fact that these you get a nice formula like that. So this formula here simply becomes you get all the factors of the period matrix from here. Okay, so I'm omitting the. Okay, I should do this. That in using this formula, you convert the 6 integrations over Teichmüller to all the 6 period matrices. And but that's this nicety stops at 3 loops. So for 1, for 2, and 3 loops, the number of independent components of the period matrix is equal to 3g minus 3. But starting at 4 loops, they are not the same. So you get 10 period matrices and you have 9 Teichmüller. And that's the Schottky problem. And in fact that is what is preventing some computations to but yeah, so people say that the Schottky problem is solved in the maths literature. It is solved at 4 loops, but I've never seen a description where I could really apply the solution there to get this done. So this is. Okay, so once you do this, you see that you will integrate that guy, and what will remain is a bunch of these lambda bars, r's, and d's. So for example, I'm going to write down what you would get from that part at 1 loop. And at 1 loop, we want to write that 3 loops. At 3 loops, we will get some contribution that looks like. I'm sorry about that. We'll have something like lambda r d1. But essentially, it's all the factors where the index in the D denotes the 0 node. So you have six factors here. And that's the contribution from doing that computation. So I'm just going to write down the summary of what has been done here. In the end, you get 1 to 6 b times Müller, and then b squared, and the calculation above shows you that this is equal to a coefficient multiplied by the period matrix, and then b 4 4 4, and then if you pay attention to the lambda bar tools, you get lambda bar to the power 12, and then that's squared. And b44 is that one. So what happened here is that, well, there are each slot here denotes one loop order. So I get 4 factors of d1, 4 factors of d2, and 4 factors of d3. So this sector here corresponds to taking 12 b0 modes from the b modes. There is another sector which contributes 11 b0 modes, where you simply replace one factor of this guy by a factor of that. So you get 11 instead. But I'm not going to show that part because it's a bit messy.
Lambda bar to the power?
Oh, it's lambda bar to the power 12. And we should not worry too much about the power here, because there will be cancellations.
Will this period matrix cover the full moduli space?
Yeah. And I should mention that in the end you get we just saw that we get the factor of the six period matrices like that, but when you integrate over the modular space of the genus 3, this is not a measure. So you need a factor of the determinant of the imaginary part of omega, the power 4. And 4 here is actually g plus 1. So we need to get 4 powers of the inverse. So we need to get 4 powers from somewhere else in the calculations, and you can see that you get lots of them from the measures, and so the zero mode the zero mode measures for the conform weight 1 variables, or the dw and so CW bar, CS, and CV. These guys, if you look at the formula of the coefficients, you get the contribution of determinant part of omega to the power 5, because this comes from the Zj factors that I wrote before somewhere. So you still have 5, and the measure needs 4, so we need still another factor of that to be able to do the moduli space integration. And in the very end of the calculation, you will get this remaining factor from integrating over. I would note like something like this: 1, 2, 3, and square. It's not something like that. Where this delta is now delta ijk is I think it was Narain or Aniban who mentioned that this is at genus 2 at some point, but now it's in genus 3, and this is epsilon omega I omega Z Zi Cj dk. It's the analogous form of the delta with two indices that appear in the two computations. So it generalizes to that, and then we use the Riemann's bilinear identity, and this computation will give you some determinate dimensional power formula. So that's where the remaining factor will come from, and then you get the 4 here, and then this volume, the volume of the moduli space was computed in general by a brave mathematician called Siegel in 58 again, and this formula here is 2 pi 2 to the 6, 5 to the 6, and 3c 5 squared and 7. So that's the volume of the moduli space, and so at every single point in the calculation we were very careful about the coefficients, and the fact that you can get control of the coefficients is a very nice feature of the pure Spinor formalism.
This is 5 squared and 7.
5 squared times 7.
365. Oh, 3 to the 6. 36. 3 to the 6.
3
Oh, 3 to the 6.
Yeah, so these are all powers. 3 to the 6. Yeah. Okay, so where am I in the computation now? The t-most. Okay, well, the computation is a bit more. I think I can erase this. And the next step in the calculation is to notice that the variables s, w, and w bar appear only in the regulator. So you can integrate them. So you will get a formula like this. S D again, this type of computation where you integrate the exponentials of W and lambda, they were done by Humberto Gomes in 2009. A very nice paper. And you can do these calculations and you get some numeric three factors here. You get, say, that factor that I was talking about to the power 22. Don't worry that in the end it will become 5. And then a product of 1 to G of a bunch of epsilon contracted with T contracted with D's, di. So I goes from 1 to 3. And squared over 11 factorial 5 factorial. Something like that. Okay, something like that. I just wrote this just to explain that you get these factors here. Epsilon tensor contracted with T, where T I wrote before, and the P's. So you get okay, so you see that the reason I did this was because this contraction here contains 11 D's. So, and 11 D's for each type of zero mode. So this factor here will give you 11 D's, zero modes. And I should have said this before, but the majority of the calculation is guided by separating the zero modes of D. And at 3 loops, genus 3, you get 16 times 3 zero modes of D, so it's 48. And from that part you get 33. So you need to get 15 zero modes of D from the B ghosts and the U's. And as I already showed here, I did a calculation for the B ghost part. This gives you 12 B's.
So how do you get those 11 zero modes from there?
Yeah, okay, because I integrate over S, and using the measures, you can show that each integration of S brings down 1 D, because, and then there are 11 S's. And then you get 11 D's from that. And yeah, that's how they appear. And so the B ghost gives you 12, and then in one sector of the calculation you need to pick 3 D's out of the vertices. And that's so I'm just going to do this schematically here. You need to do so that there are 4 vertices: U1, U2, U3, U4, and you need to take 3 D's. And the way to do that is, well, you by now we can do P's very quickly and look at the zero modes. And for example, we will get DW12, DW3, DW4, and then we did one OPE, that's del G12. The Green's function. And then plus all the other possibilities, where 1 and 2 can be chosen out of the set with 1, 2, and 3, and 4, by all possible combinations, so you get a bunch of terms. But that's how you pick 3Ds out of the vertices, so that's how you get the W1, 2 that I mentioned before. So finally, you will need to, at this point you will have something that looks like this. You will have an integral over all the zero modes of D, and then the factor that comes from there, so 11 D's from here, and then the biggest part is 4, 4, and 4 that looks like that, and then finally the 3 guys from the vertices. Plus permutations. So we need to do this integral. But this integral here is quite easily done because it's a fermionic integral. And so in the beginning of the paper we wrote down what you get once you do this with, so that there are 11 here, and then you need 5 additional variables that will come from, okay, so, and then this integral here is a coefficient that depends on the CD normalization, and it will be proportional to that T tensor. Something like that, there is a number. But, so for example, you get 11 Ds from here, 4 Ds from there, and then you need to distribute all the 3 different Ds out of the vertex. So for example, you can choose 1, 2, 3, like that, and then this separates correctly this integral here, and you get that for each zero mode integral, and it's this computation here that gives you that monster that I wrote in the beginning, where you have many lambda bars, and where the lambda bars coming from? They are coming from here with R's, and you get many lambdas from here. Each T contains 3 lambdas, so you get 9 of them. So these integrals will contribute 9 Ds, and the B's contain 6 lambda bars, and that will give you that structure as well. So it's quite some computations to do, but at this point here we had good control of the integrals, and because in the end it's just a bit of combinatorics. These computations are not complicated to do. In fact, they are trivial once you get the measures correct. Questions? We are approaching the final moments. Okay, so I guess I went a bit now my notes are over and I need to look at the paper. But the calculation is essentially done. And the end result is you get, say for example, when you do these integrals here, the result is you just define a name for what you get, and that's the name we chose. That's this guy is defined by this computation, and it has that form that there was before. And so at this point, the part of the calculation with the 12 D0 modes is proportional to these results. And now I'm going to write the numeric factors: 23, 326, and then the coupling constant, 4 powers of the dilaton, and then alpha prime to the 6, and then T volume, and then C3 minus 10, the integral over this guy K12 squared, and then minus 3, I need to explain that, and then times the Covariant factor. So you see the calculation is not really that complicated. You hide all the there is some structure here, but it's I need to tell you what K12 is. K12 is plus permutations, and I didn't mention, but okay, so these are all the permutations of that form, and then there is still another set of terms where the vertices still contribute 3 Ds, right? Okay, so I should have said this at this point, but let me just mention that very briefly. I said that the vertices U1, U2, U3, U4 need to give you 3 Ds, and there is another possibility instead of doing that. The other possibility is you take a 0 mode of pi m from one of the vertices. So you get, let me call the 0 mode of pi m Lm, it's the loop momentum, and then say I take from 1, and then dw2, dw3, dw4. That's another type of contribution that should be there. So, and this part here, you also, you do the same type of calculation, and you will get, and you define a name like that, and the name that we chose was L. So that there will be terms like these, 1, 2, 3, 4, and then L, M, 1, 3, 4, 2, plus L, M, 2, 3, 4, 1, plus other terms by permutations. And I didn't explain what this guy is, but it's basically the old delta multiplied by the loop momentum. So that's why you get a factor index there. So that's K12. Okay, then you repeat the same steps for
At
the...
this stage, we have already made the low energy approximation, right?
Yeah.
The modes.
Yes.
Then why are you keeping the full K covariance factor? Could be approximately.
Oh, okay, no, because at this point you simply cannot set it to 1 by brute force, because there is still these guys around. And so you need to integrate these against the convolution factor to get vectors like that. Okay, so that was the 12 zero mode part of the bigos. There is still the 11 zero mode part. The calculation is a bit more convoluted, but you can do it in the same way, and the result that you get is quite compact. I would say it's something like K11. It's Sn 1, 2, 3, 4, and then delta n 1, 2, 3, 4 plus permutations where this Sn looks similar to the T that I wrote before. It's also a bit messy to work with, but you can do the calculations. So finally, when you sum the K11 with K12, take the holomorphic square and all that, you will get the amplitude. The amplitude is okay, some numbers here, and then the omega, and then the determinant of imaginary part of omega to the power 5, the integral over the z's of f squared plus t squared times covariance, where f squared is essentially K12 squared, and t squared is essentially K1 squared, but now, okay, it's not that, but because you see that there is a contribution where these guys talks to that combination. So the 11 zero mode part talks to this part of that comes with 12 D0 12 equals zero mode. So, and then tensor, which is the combination of these L's with S, and the precise combination is this one. And I'm not going to be able to explain why, but it happens that this particular combination with that precise coefficient is nicer than the composing tensors. Because these guys satisfies more symmetries than the combination of in the individual parts. Okay, so and this factor here comes from one of the contributions is that you got rid of 192 from that part and you replace it by 2, and then the calculations are a bit different at some points where, for example, the b goals will be different, but then you get that precise factor, and that was also a nice consistency check in at an intermediate step, simply because when the factor here is precisely that one, then you get the nice properties of t. And so, okay, but that's a very internal consistency check. Because in the end, there is still some beauty left out of the calculations. And that's one point where you see something going on. And then finally, okay, so now I'm not going to be able to explain, but this part here, as I mentioned, you will get some inverse powers of Mendelssohn from that from that integral, and the clean way to do this analysis is by using integration by parts. And but these are done in the appendix, and my short-term memory didn't arrive at that part of the paper, so I don't remember everything by heart. So I'm just going to write down the result. Okay, so now we do this square integral with the formalism factor. Okay, I should probably, okay, now and then that's so this part here, you integrate over the surface, and what's required you to do here is you need to integrate over these guys here using the Riemann bilinear identity, and you get minus 12 pi alpha 2, and then k, and then finally the determinant of omega, like that, and then plus order alpha prime squared. And sadly enough, this is where the original factor of 3 mistake was made in this simple calculation here, where you just use basically something like that. I cannot explain why. Yeah, so in the original version of the paper, this factor was 36, minus 36. But yeah, that's why. And k over there is now t to 3 1 4 squared over s to 3, and then plus all the other six channels, where you simply replace s to 3 by s12, s13, and so forth, all the six guys. And as I mentioned before, the dimension of this guy here is del this to the 6th r to the 4th, and yeah, so you get this, and finally this pure Spinor bracket here is the I'm going to say, it is still the 3-level version in the minimal computation. there are these zero modes to do here of the stuff that was written down before. And let me just mention a point in the calculations that was really hard to do. That was, well, if the whole paper took, well, that part of the calculation that I'm going to show here now took like 90% of the time that took to do the calculation. And this is the part related to this guy here, Lm. Because Lm, roughly speaking, has a factor of lambda bar d to the 6th, and then Am multiplied by Am www. And that computation is tricky to do, because when you hit the covariant derivative on A alpha, Am, there will be one term which is the momentum Am times A alpha. And then the next time you hit with a derivative on A alpha, you are stuck, because you cannot get rid of the derivative, because the equation of motion of A alpha does not get rid of the covariant derivative. And then you get a mess. And if you try to do the calculations covariantly, because of that problem, I said, well, there was no easy way to handle the computations. And then finally, one day, reading about twistors, we looked at the paper that Nathan mentioned this morning from 2009, where he described the gauge A alpha he wrote it like that, where H, if you contract with the momentum, is 1. And then when that was, soon after we read this in the paper, then the calculation was over. Because now D converts W to F, and D of F converts back to W, and then it's a matter of just W, F, momentum, W, momentum, F, momentum squared W, and so forth. Then you can do the calculation, and that was how it's done. But the sad thing is that you have this guy, but in the end it cancels, but you cannot see this cancellation until the very end of the calculation. That's what is a bit early about doing the computation this way, but that's how it was done. So, for example, in the form of the Lm, you will see the age is there in the component form of Lm, which I think was submitted to the archive together with the paper. Finally, and at this point the calculation is done. So you add that part with the part coming from here, you sum them and you get the answer. And so that's how the story went, and the final result is A3 is equal to 2 pi like that, 4 pi 3, 2, 6, and then S 1, 2, 2, S 1, 3, 2, S 2, 3, 2, K, K bar. Right, K bar is proportional to T8, F to the fourth.
It's T bar 4 lambda. That's T bar 4 lambda.
Yeah, well, lambda is, it's unfortunate that we use the letter lambda, but it's the Dirac. It's the usual exponential of 2g minus 2, or no, okay, g minus 2, 2g minus 2, oh my god, 0, oh no, there's something wrong. I cannot, what's the power of the open constant?
2g minus 2.
Yeah, 2,
Okay.
okay.
That's G minus 1, yeah.
2 times g minus 1 inside the bracket.
Okay, yeah, 2, yeah, so that's the power there. Yeah, and then that's the final result up to higher orders in alpha prime. And then we also had the computations of the in 2010 of the two-loop amplitude, which is similar here, and then was S squared, T squared plus U squared, K bar. And we also had the one loop with all the precise coefficients and the tree level. And then we simply checked that the ratios of these amplitudes here match with the escalating predictions of Michael Green and Pierre van Hove. But yeah, it's was a tour de force, and we could simplify a lot of the computations, and in the end, well, we got a result. The computation could be done, and the formalism and us survived. So that was a nice confirmation that the formalism is in the right direction. Questions?
The last one is A plus A6 and F4.
Oh no, yeah, that was just mentioned that this K is okay. K, if you do the calculations correctly, it's 2 to the power 3 times 2,880 S12 S23 A n views 1, 2, 3, 4. The 5.3 loops, it's unpublished, but there's still some factors to work out.
But it's doable.
Yeah, it's doable. In this limit, it's doable. Oh, it's okay. I now I remember where I stopped. It's because at 4 points you get one vector contraction, and for 5 points you will have two vector contractions between left and right, and that's a bit more complicated because, well, as I mentioned before, the kinematic factors are not really optimized to, they are not user friendly yet. But
But the
it's
lambda bar denominators don't cause any problem?
no, they don't cause any problem. I can show what's the maximal what's the maximum power of lambda bar? Well, I should probably be able to do this by simply counting okay, no, well, it's, okay, at some point I rolled this -3 over there, right? And that -3 counts the power of lambda bar in the pose, and that there is a definition in the beginning of the paper where we explain that it's here, and okay, so the final integration over this measure here with lambda bar involves the power, it involves a correlator with -3 here, and the definition is so -3 is, will give you all the lambda bar, blah blah, and lambda bar to the power 6. 3 minus, yeah. And the definition of this bracket here is the measures and then the m, whatever is inside there, with the power here is 3 minus n, where n is that type, and so you get, and then minus lambda bar r theta. And again, okay, so the maximum power was lambda bar to the 6, which is still okay to integrate. And again, this type of integrals was beautifully analyzed by Umberto Gomes in 2009, and the result that he got for that lambda bar part is then is a lambda bar to the power n e minus lambda bar, that's equal to 7 plus n factorial, 7 factorial times 60, and then 2 pi over ag to the power 11. So in that paper, 2009, he didn't have this factor here. He simply used some normalization for the one loop case, and but this factor of 60 here is a very non-trivial calculation that he did. It's related to the first Chern class of the pure spinor pure spinor space SO10 of a U5, and it's a very nice mathematical paper, I guess. I think is so yeah. So that's one of the.
What's the reference for that? What's the reference?
Oh, the reference I wrote before, but I can write again. It's 0910 7405 by Humberto Gomes, and that was, I think, his PhD project with Nathan. And yeah, so that's basically, hopefully in the future this calculation will be much quicker.
What's the question you were saying for the 5 point? I mean, is restricting only to 0 modes of p is good enough? It doesn't, because with as you go to higher number of points,
Yeah, the assumption you make is the same, that you are just considering 0 modes of the d-modes, and these will give you the leading order corrections.
so the minimal endpoint also will be doing this.
Yeah, but at this level, with this language, with lambda bars, it's messy. The idea would be to understand, to get some pattern for the generalization here. But right now, I'm more motivated to look at the type of the minimal Spinor superspace expression that corresponds to these guys. So, for example, I wrote the expression for that one in the minimal superspace, but this Tn will be basically 1, 2, 3, 4. It's basically this guy here, 2, 3, 4, plus permutations. And now you simply don't have any problems computing this guy which were related to the covariant derivative acting on AM recursively. We simply, this takes less than 1 second. You're done. There's nothing here, and you can immediately check. Well, that there is actually another term like that, 2, 3, 4 here, but that's about it. You can immediately compute the BRST variation, and you get a nice algebra for that. So that's how I think the generalization to higher points should proceed. It's by using the stuff that you can easily understand the patterns. And yeah, so, and recently in April last year, we also did together with Oliver Slaughter and Humberto Gomes, we computed the 5 point at 2 loops in the lower energy limit. And the idea there was, well, my motivation was simply to understand more about how to do these manipulations, but in the very end you can get a number out of it and compare with S-duality predictions, where I kind of it's the same. The Eisenstein series here is the same one for the 4 point. So you compare the 3-level prediction from here with the 2-loop computation that we did, and everything matches. But this matching of these numbers here were not all that of a check, because you can easily obtain the number by factorization. But the reason to do this calculation was just to get a handle the content. And in fact, in this paper here, we already simplified a lot of the mechanisms here. Were done in 2013 by some. We were just doing the calculations, but now they are more organized because of this paper here. But yeah, so 5.2 loops in the non-minimal yes is done, and you can probably do 6 points, and at the low energy level now nothing really is new to. Well, they are not. Okay. We should do this calculation and see if we get some pattern out of it. Because one thing that I had planned to discuss today was the low energy limit of the one loop amplitude. Because in 2012, together with Oliver Slaughter, the paper is 1203. We computed the endpoint. We obtained the endpoint result for the one loop amplitude at the low energy limit, so the leading order term. So at one loop, this pattern was easily recognized. It gave rise to very, very nice structures like the scalar BRST invariants. So the one loop at endpoints is basically written as a sum in the low energy limit. So okay, it's basically a sum over multi-particle BRST invariants multiplied by some worksheet functions, and that's it. And then there are the Stirling number n1 minus n-1 with it's the unsigned Stirling number of order 3 or something. That's the number, and of independent BRST invariants. So it's 6 for 5 points, 35 for 6 points, 225 for 7 points, and so these numbers count the independent BRST invariants. And so BRST invariants, I mean the QC equals 0. And just as an example, the 5-point BRST invariant is written as M1, M2, 3, 4, 5 plus M1, 2, M3, M4, M5 plus M3, 1. The BRST variations of the multi-particle M like that, this M with 3 slots is essentially of the form lambda gamma W, lambda gamma W F. That was in the paper by Nathan in 2004 for the one loop amplitude. And you get things like the BRST variation of this guy using the multi-particle superfields is 3, 4, 5 minus 3 and 2 and 4 and 5, and this M here is the one from the previous lecture, so you can easily check that this is BRST invariant. And in 2012 we understood the structure of this guy for endpoints, but last year, no, 2 years ago, but now it's 2014, so it's a paper by 1408. We found a recursive construction of BRST invariants, where simply studying the BRST algebra here, we may I just use 5 because this is interesting. There is a recursive construction of these guys. We basically defined an operation like this, where I is a single particle label and A is a multi-particle label. And if you define a concatenation like this, I, A, then, for example, that guy over there is M1, M2, 3, 4, 5 plus M1 tensor C2, 3, 4, 5, where C2, 3, 4, 5 it's the guy here for 4 points. It's essentially the kinematic factor that Nathan found in 2004. So that's and then that's easily generalizable for A, B, C indices. You simply replace A, whatever you have there by the multi-particle label. So without even doing any string calculations, you can know a lot about the kinematic factors. We also have generate recursive constructions of scale of vector BRST invariants, where Q of these guys is 0, and then something very interesting happens at the tensor level, where Q on this guy is no longer BRST invariant, but there is a trace part which is related to the anomaly factor. Something like that, where this Y appears, well, not with this name, but it's essentially a structure with lambda 3 and then lambda gamma W that it's in a paper with Nathan from 2006, 06, 07 something. So, and then this is generalizable to endpoints, to n tensors, and I mean there are a lot of things that I could talk about this, and it's very interesting because the structure simply came from, okay, suppose that you just take 0 modes out of the big ones and analyze what happens for endpoints, and that's the structure you get. And there is another thing that it's worth mentioning about the scalar C's, is that there is now a very beautiful closed formula that involves the shuffle product or something. You can write it using the shuffle product or a row map from the math literature that rewrites the scalar C's as a combination of S squared A and B's kinematic factors. So say something like C1, 2, 3, 4 is S12, S23, A and B's 1, 2, 3, 4. So there is a closed formula for that. There are very nice Lie algebra structures here, and the end result is that, okay, the low energy limit of one loop amplitudes can be written in terms of Young-Mills 3 level amplitudes, but that's no longer true for the non-linear part because of this guy. So it starts to hit you in the face at 6 points. You get the anomaly part, and this guy cannot be written as an use amplitude. But there are all sorts of structures that start to appear once you study higher point amplitudes. But for that it's essential that you have a good control over the superspace. So this one paper here is done in the minimal pure Spinor setup simply because it's minimal. You get the lambda free directly. There are no lambda bars and derivatives to consider. So that's why I think one direction to understand three loops at endpoints would be to generalize the simple expressions I mentioned before.
This one loop terms are all 4 derivative terms? When you took the limit, yeah.
It's of 4 derivative terms. You mean T8 f to the 4th?
Yeah, I mean number of parts
Yeah.
of momentum is all.
Yeah. Okay, so yeah, that's another thing that there is a nice pattern going on here, which is this is unpublished, but it's okay. Say C1, 2, 3, 4. If you compute the components, that's T8, and then let me write it like F1, F2, F3, F4, right? So now what happens with this guy? What's the component expansion of that guy? And if you use the component Bernoulli current, or in this case, yeah, it's the Bernoulli current. So at the component level, not at the superfield level anymore, you get F1, F2, 3, F4, F5 plus T8, F1, 2, F3, F4, F5 plus T8, F3, 1, F2, F4, F5. Which, by the way, I'm simply translating this formula to that. This is not true at a particular term, like this is not equal to that, but in the BRST invariant expression, the sum of the three naive translations gives you the correct result, and that is also easily generalizable and in the same way as that. So, and by the way, this is how the RNS computations should be organized. So that's why, for example, I mentioned yesterday that, okay, the RNS is a bit messier because you don't have superfields, but now you have the component, the Bernoulli currents and all that, and then the RNS should be organized using those component superfields. So probably U1, U2 will involve if you analyze that in the RNS, will probably give you some way to write in terms of component Bernoulli currents. And this is one evidence that this is the way to go.
Yeah, I'm wondering whether there is a way to understand this from the effective action viewpoint. That suppose you just say the effect of one loop correction is to correct the coefficient of the R to the 4th term at tree level. Right? Could we have thought of it that way and then just see what the tree level Feynman diagrams will give with this corrected coefficient?
Okay, I'm sorry, I did.
Yeah,
Okay.
I'm just saying that the structure of the one loop 4-point function is the same as the tree level 4-point function, right? The
That is,
T8 structure.
Okay, so yeah, but it's a bit yeah, okay, yes, because of this. So the C's that you get at one loop can be rewritten in terms of Young-Mills trees.
Which are also related to superparametric trees.
Yes, but that is no longer true starting at 6 points because of the anomaly. So naively, that's what would happen, but there might be subtleties if you just proceed naively. Well, there are more things I could say. For example, I have prepared some notes about the BCJ identities at tree level, and pure Spinors really simplify finding the numerators that satisfy BCJ in a local form. This is, I'm obviously a bit biased to say this, but I think that the description in 10 dimensions of the BCJ numerators is the cleanest of all. You get closed formula solutions for the endpoint numerators that satisfy BCJ. And the numerators simply look like V12, V3, V4, they are very compact. And yeah, okay, so I guess that like Nathan said this morning, that life starts with 10 dimensions. I think I'm going to use that quote from now on. Yeah, so the idea, well, the whole idea with pure Spinor superspace is to actually realize that vision that life starts in 10 dimensions. By you compute the amplitudes in 10 dimensions, they look simple, and then from that you reduce to 4. And so that's why, for example, the lecture where Nathan mentioned that twistors twistors in general are pure Spinors is an indication that might be possible, because, well, pure spin, we are all talking about pure Spinors in 10 dimensions, but according to Nathan, everything could be like twistor superspace expressions, and so there must be some nice way to rewrite these things by understanding them as twistors. And looks like there are a lot of things to do, and I hope I motivated some of you to work on these, and let's see what the future reserves to all of us. So that's it. I think I'm going to stop.
Any further questions? Okay, so let's thank Carlos once more for the excellent set of lecture.